Question 13. Okay, in question 13 we have four forces. Now, four forces is a bit daunting for some people. Let's have a look at what that looks like though. We said we're going to do force. You know, I'm going to make a change. I'm going to say that the raw force is black and then the components are going to be blue. I just like that better, right? So I know it's inconsistent, but when I do this with my daughter, she's like, you know, at school, you kind of have to use just one color all the time. Like, it says blue or black pen. And I'm like, yeah, I know. I'm like, but yeah, ain't at school. Okay. 100 and 200. Okay. If you look at the drawing in the example, they haven't drawn their vectors to scale. Yeah, they haven't drawn their vectors to scale. Me, I have drawn all of my vectors to scale. Do you see how this one is a little bit bigger than that one, and this one's a lot bigger? Do you see how that they kind of all match up? I obviously haven't used a rule or a protractor. You guys could do that, right? You own rulers, you own protractors. You are allowed to draw these things. Now, I'm going to tell you the angles. I'm going to use green for the angles. This one here, 45 degrees from the horizontal, and this one here is 30 degrees from the horizontal. The others are in the X and Y direction. Now, I'm going to tell this as a story about a hiker, and I'm just going to add in all these forces. So once upon a time, there was a hiker. Which one do we want to start with? We want to start with north or east? North. Okay, once upon a time, there was a hiker who went 120 units, proprogs perhaps, if you've seen Gilmore Girls, or you're familiar with the law of Yale University. Proprogs is a non-standard unit of measurement. Okay, which direction are we going to go with next?
300.
300, I'm glad you said that. Okay, 300. Did you see how I transferred that angle? I'm going to teach you how to do that with a ruler. And yours is going to be way more accurate than the thing I just messed with, right? I've just transferred that angle directly across, because, you know, pretty good at this. Okay, the next thing, okay, I'm going to tell you that actually before we went up 120, we actually went across 180. And then after this, so the hiker, let's say the hiker went 180 to the west, 120 north, and then 300 northeast, and then the hiker, the last thing she did is she went 200 at a bearing, if we're using the hiking analogy, at a bearing of 90 plus 30, 120 degrees. Yeah? So like east-southeast or something, very close to east-southeast. Okay. Then, the hiker wanted to know how far she was from where she started. So I said, well, okay, you started here, and you ended here, and then I just took my ruler out and I measured. Just took a ruler out and measured. And I said, well, if this is 200, it's probably about, I don't know, about 400, maybe a bit less. Let's say 370, right? 370 proprogs away from where she started. In our case, we're actually doing newtons, but the idea is the story works. I think a lot of people find it easier if you use this hiking analogy, right? So she was, and I'm going to use the directions. I'm going to say that she's roughly, the resultant is roughly 370 newtons in our case, and using our directional coordinate system, she is northeast. Northeast of where she wanted to be, or where she started. Now, in other questions, you might be asked to find the equilibriant. The equilibriant would be asking, how far does she need to go in order to get back to her car and go home? Yeah? How far does she have to walk back if she went in a straight line to get back to her car? Now, we've been asked to find the resultant, so we're going to use this method. Now, what I'm going to do is, we're going to go back to use blue for the direct. Okay, I did this whole. Never mind, everybody. We're going to draw our rectangle again. Okay, we've got our rectangle. Excited? That looks a good looking rectangle, if I do say so myself. What are the values of our rectangle? Well, this one here is pretty easy. That's already 120 up. There's actually a rule in engineering that we're always supposed to write to the left of the line or above the line, right? Or if we're writing in dimension. So if we're going to write here, I'm going to use my green. I'm going to dimension this like this. Just to get you used to dimensioning. Okay. Now I have the Tahitian KFC song in my head. Okay, one last one. Okay, this one here, pretty easy. We've already been told this one here is 120. This one here is 180. We already know that. What do we know about this one here? Let's drag it out. Let's drag, we'll call this value here, we'll go A, B, C, and D. Let's drag B out here. Let's go, it's... Okay, if that's 300, and the angle is 45 degrees, is this adjacent or opposite, this side here? Is it adjacent or opposite? Adjacent. So we're going to say 300 adjacent is going to be Soka or Toa. Adjacent is cos, the hypotenuse cos theta, which is going to be 300 cos 45. But me, because I'm a computer, I know that that's 300 0.707. I actually have to type it in my calculator because I'm not that great at computer. Okay. This one here is going to be dot 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 dot. What side of the look?
Opposite.
Opposite. So it's going to be hypotenuse what theta? Opposite. Soka or Toa?
Soka or Soka?
Sine theta. Excellent. Okay. Well, sorry, theta. I should write theta there. Okay. Which is equal to 300 sine 30, not 30, 45, good work, Luke, which is 300 0.707, because I've learned that number, I've done this enough time. Okay, somebody has put this into a calculator. Marcus, tell me, what are these numbers?
The 300 plus 45 is 212.1.
212.1, beautiful. And you know what? This one's going to be the same. Can save everyone the calculation. 212.1. Because 45 degree angles, they're isosceles. Yeah, 45 on both sides. So it's the same. Okay. To be honest, we're just going to go to the nearest Newton. You maybe would keep the actual values, but for me, I'm speeding things up. Okay, so we're going to go now to C. Let's have a look at C. I'm going to break C up. Okay, C is 200. And just to save everyone a little bit of time, this one here, if I tell you this is 30, this is adjacent. So adjacent we use hypotenuse cos 30. Cos 30 is 0.866. So this is going to be equal to 200 0.866. This one here is going to be equal to 200 times 0.5. So So I'm going to write that over here. This is going to be 100, and 200 times 0.66 is going to be 173, right? Because it's root 3 times 100. Okay, what values are we missing? Okay, so can someone tell me how tall is my rectangle? You'll need a calculator. How tall is my rectangle?
352.
Tall. This is 120.
332.
332. Yeah, that sounds right.
Oh, yeah, right.
But I was just about to write the wrong thing. So, yeah, 332. So it's this number plus this number. So what's the missing value then? What is this value here? What's this value here? 222? I couldn't hear. 232, that sounds about right. Okay. 232. Okay, what's this value here? Well, what's the width of our rectangle? What's the width of our rectangle? That's what I get, 385. Okay, so that means that what's this value here? It's going to be 385 minus 180. 205 sounds right. I did an estimate in my head before I typed it in the calculator, so that way, if I got an answer wrong, right, I'm going to catch myself before it gets too far out of hand. Okay, so I've got Charlie the robot. No, it's actually not Charlie the robot, it's Eddie the robot this time. I wish I hadn't had, for this entire question, my terrible estimate up on the board the whole time. Because there are going to be people who are watching this video thinking, where the hell did that number come from? And it was just because I just literally estimated and I didn't, ask someone to look in the back of the book like I'm about to do now. Can you tell me what the actual answer is?
310.
310? Okay, so what we're going to do is we're going to say our resultant looks like this. It's a little taller than it is wide. If it's a little taller than it is wide, what does that mean our angle is going to be? Theta is going to be roughly equal to what? If it's a little taller than it is wide, the angle is going to be... If the angle is exactly equal, it's going to be 45 degrees, right? So if it's a little bit taller, our angle is going to be a little bit bigger. So it's going to be maybe 50 degrees or something like that. Let's have a look. Okay, so we've got 232. And we've got 205. Luke, how am I going to find this value here?
Pythagoras.
Exactly right. Okay, so I'm doing 205 squared plus 232 squared. I'm going to take the square root of all of that, and I get an answer which is R equals 309.5, which is 310 newtons. I was out by a fair bit, but I was also eyeballing, so I'm going to allow that. I'm going to say that. I just wish they hadn't written on the board for so long. Theta equals what's our angle going to equal? How am I going to approach that? Riley? What function?
You do... Yeah.
Starts with T?
The 10 minus 1 thing.
Inverse of 10. I gotcha. Okay. The opposite over the adjacent. The opposite is?
232.
And the adjacent is?
Over 205.
And if our number is less than 45 degrees, we're going to have questions. We're going to say, calculator, what are you doing to me? I get 48 degrees. I'm happy with that estimate. 48.5, I'm going to round that up to 49. Okay. That's our answer. Sarah. Good. Okay. There's one last question in the textbook that's easy to solve. Well, I wouldn't say easy to solve, but it's in the same vein, and then I've got it on Facebook for you. I've screen capped it. But I'm going to look at how much time we have. Yeah, I don't think we have enough time to solve the whole question, but what we'll do is we'll just draw it up and have a quick look at it, and then I'm going to talk to you about the 3/4 method. Okay, so Now, there are alternate methods to using this rectangle method, right? As I've said before, I have a question where I've done a question from a past paper where I used a whole bunch of animation and I did it as a table, you know, but I found that intuitively looking and saying how tall is the rectangle, what's the missing side, it just works, right? Now, for this last question, question 14, an old lamp hangs from a roof using wires. What will the tension of the cables be if there's a 10 kilogram lamp? A 10 kilogram lamp, well, we don't really use mass in our subject. What do we use instead? We don't really use mass. What force, when we're measuring forces, mass is not a force.
Gravity.
10 times gravity. So we could use 98 newtons, that would be more correct. You know what, for the sake of argument, I'm going to use 98 newtons, right? 98 newtons is going to be more correct. And that will help people to remember, where did that 9.8 come from? This is equal to, so the W equals 10 brackets 9.8 for Earth's gravity equals 98. But if you said 100 newtons, I would 100% be okay with that. And you see HSC answers, they're kind of 50-50. Sometimes they use 9.8, sometimes they don't. I don't really like my, there we go, done. 30 degrees, 15 degrees. Now, they've labelled this as A, and this is B. I'm going to call this one here mg, which is what I typically call weight. I don't use W because W can be confused with work. Our vector diagram here is going to look something like this. I'm going to take this same angle, and I'm going to take this same angle, right? And the reason I need to do that is because this here is pulling in this direction, and this one here is pulling in that direction. So here we have this one going up. Now, a way of thinking about that is if I have a dot, are these going clockwise or anti-clockwise around the dot? Clockwise or anti-clockwise around the dot? Excellent. All right, so if they all need to be going anti-clockwise if we're looking at three forces. Because this force here, this is in equilibrium. Everything is in equilibrium. There's no resultant here. We're being asked to find what is the tension because this thing is in equilibrium. So we're going to say this one here is mg. mg equals 98 newtons. But we don't know these sides. But here's what we do know. We know this is this angle here, this is B, is 15 degrees, and that this one here is 30 degrees. What's the value of this angle here? Alternate angles on parallel lines. So this one here is going to be 15, excellent. And this one here is going to be 30. So, some quick maths, people. What's this value? This has to be 60, so this here is 60. This here is going to be equal to 45. This angle here is going to be equal to, this is a complementary angle, it means it adds up to 90 degrees. Yeah? 75. Yeah, 75 plus 15 equals 90, that sounds right, don't want to be wrong on the internet. Okay, so if I know this angle here, let's call this one here big M, right? That angle is M. Let's call this angle here, well this is, here is A, this is vector A, so this is big A, this is vector B, so it's big B. So what we can say here is, which one do we want to find first, A or B? A. So side A, I always write my unknown on top. Side A is equal to sine A. Side A with a D over sine A with an N is going to be equal to side MG over sine angle of N. Now I'm going to replace things with stuff I know, right? Now what I know, I don't know A is unknown, but I know angle A, sine 75 degrees. I know MG is 98. I know that the value of m is sine 45 degrees. Then what I can do is I can say A equals 98 sine 75 divided by sine 45. And that will give me my answer. Anyone who has a calculator, they could do that for me, or I could just walk over here and look at the book. 14. 133.6. But no, I'm quite happy with 133. 133 newtons. Okay. The process for B is the same. Yeah. Now, I said at the start of the year, I don't really use the sine rule. I never use the cosine rule. Cosine rule, that's, that would require like actual maths ability. I would typically just draw this because the whole thing is it's drawn to scale, right? I would just draw it. I own a protractor, right? I can just measure, right? So if you're not confident, if you are looking at this and I have no idea what is going on, just remember you are allowed to just draw this and just say if that's 100, well this is a little bit more than 100, yeah? And you can just draw it to scale and just figure it out that way. So there's different ways of approaching these questions. Okay, so I had two questions that I didn't address earlier. The first one is, so what are we actually finding here? So what we're finding is the tension, and so we've said that this is cable A. We want to find the tension in this cable. So the reason why we care about the level of tension is the same as if we're doing a tug of war, and if we've got two kindergartners do a tug of war, we can get by with a much smaller rope than if we have two teams of army dudes doing a tug of war. We need a much thicker rope because otherwise they're just going to snap the rope. In this case, we've only got a 10 kilogram weight or a 98 Newton weight, causing this to have a load of, there's more load on this cable of 130 newtons. There's more load than if you just had, because of this angle, there's more load than if you just had the 10 kilogram weight on the cable. It's interesting to note that there's more force on this cable than if you just had a rope holding a 10 kilogram weight. So there's tension on this cable, and you can think of that as there's something trying to snap that cable. So if we used, say, a line of cotton thread, obviously it's going to snap with a 10 kilogram rope. If we start using piano wire, maybe we get away with it, but a 10 kilogram weight or 100 newtons might snap with that amount of weight. Whereas if we're starting to use steel wire, or even better, a chain or a cable or thread, a wound spun cable, we're going to be more able to support that level of that load. So that's what we're finding. The next question is, but why are the angles going in this direction? And the idea is that, remember, we have to preserve the rule of tip to tail. So if I have A, I always like to start with down, right? Weight, gravity is down, right? It's the definition of down. So if I know that this is down, if I have this dot, everything else needs to be following that same direction. If this is going down, and was this going clockwise or anti-clockwise? Anti-clockwise. So they all need to be going out anti-clockwise because we're finding three forces in equilibrium. This lamp is not moving, it's not falling, it's not collapsing, it's not broken, it's not moving, so it's in equilibrium. We want to find three forces in equilibrium, which means that all of these forces have to be going in that same clockwise or anti-clockwise direction. Another way we phrase that is saying that the arrows need to be tip to tail. It means that the head of the arrow has to be touching the tail of the next arrow. The head of this arrow has to be touching the tail of that arrow.